This is a lesson about magnetic forces on current distributions and a unit on magnetism. In a prior lesson, I had talked about forces on moving charges in magnetic fields, and that is the basis of this lesson as well. What happens is a current is a moving charge, right? A force on a moving charge in a magnetic field is given by this equation. If I think about velocity being a differential of displacement, I can write this instead as q delta x over delta t and cross that into b. And it maintains that whole equation. What I'm going to do is move the differential. Instead of it being in front of the delta x, I'm going to put it in front of the q. So I get delta q over delta t, and you may see that and remember that that is current. An amount of charge over an amount of time is current. And then I still have some sort of distance in here, this x equation, we call that L, and you can see that in the equation down here, and cross that into B. And so this equation for forces on currents in magnetic fields is not a different force, it's a rearrangement of the equation to recognize that I can look at a current having a force on it. We're going to use right-hand rule very similarly as we did with forces on charges moving in a magnetic field. On a current, instead of putting our thumb in direction of the velocity, we're going to put our thumb in the direction of the current. The fingers are in the direction of the magnetic field, and then the palm gives the direction of the force. And we're going to note again that this force points perpendicularly away from the plane that's formed by the current and the magnetic field. You'll have some examples of how to do right-hand rule for this in homework or other examples. So I wanted to show you how to calculate the magnetic force on currents. It was a cross product, and we know for cross products you take the magnitude of the two vectors and then multiply by the sine of the angle between them. And this is known more commonly as the Bill equation. Technically it would be ILB sine theta. That's what I had on this prior slide. But we can rearrange it, Bill sine theta. B is the uniform magnetic field throughout this region, not just at this point, but throughout this region. There's an external uniform magnetic field. There's a current going through that, and there's usually a wire of some sort that you would arrange, you would align your thumb along. There is a length of that conductor. So in this situation, you would be given some length of that wire, and that's what L means in this equation. Again, we're going to use right-hand rule for positive charges, which means conventional current. So in this picture up here, when I see I am going to think about this in terms of conventional current, and this is the positive charge motion. For a negative direction, for negative charges, you would flip the result. So now that we know how to find the magnitude and direction of the magnetic force on a current, let's look at an example. And I tried to pick an everyday example here. It says a DC power line for a light rail system. So public transportation, the light rail, carries 1,000 amps at an angle of 30 degrees to the Earth's 5 times 10 to the negative 5th Tesla field. What is the force on a 100-meter section of this line? It seems like if I have just one charge, it's not a very large force, but now I have 1,000 amps, which is a lot of amps. It's a really high current, actually. So let's put this equation together. We have the magnetic field. They give us 5 times 10 to the negative 5th. The current they give us is 1,000. The length they give us is 100 meters, and they tell us that the orientation between them, and I'm just going to pick if the north is in one direction, the current is this direction, there's a 30-degree angle between them. So when you calculate this force, when you run this through your calculator, you get 2.5 newtons. And if you're familiar with newtons, this actually is not a lot. If we think about this in terms of weight, it would be 0.255 kilograms, about a quarter of a kilogram, or if you multiply, if you want to get that into pounds, it's about half a pound. So it's not a lot, but I think I'm concerned for that much wire that's over a period of time, that probably would cause some sort of drooping, some sort of deformation in the wire. Maybe the quality of the wire would become compromised, and the ampage, or it might create danger, because that is a really high ampage to have a damaged wire, a compromised wire with. Reducing the magnetic effects sounds like it would be a good idea in this situation.